topic is like my absolute favorite, like I said. But the key, the trick to being able to do these problems is writing things down. Okay? Showing work. The math is not that difficult, but it's kind of like that last problem we did on this handout you turned in. You know, once we wrote down what all of our variables were, we were able to just plug them in. But sometimes you might be looking at a problem that has 6 different numbers, and if you're just trying to plug those all in without taking the time to write down what everything is, you will make a mistake. Okay, so when we go through these, we are really going to be showing all of our work, writing everything out to make it very clear how we're getting to an answer. So a related rate is basically just talking about 2 or more quantities that vary with respect to time. Okay, if I took a ball and I threw it like diagonally, I could measure how far horizontally it moved and how far vertically it moved, right? And both of those things are changing over time, right? After 1 second, it's increased this much vertically and this much horizontally, and after 3 seconds, that number has changed. Can we all agree with that? So it's taking multiple quantities that change over a period of time. So when we're looking at those, we'll be talking about derivatives because we know derivatives are a rate of change. But we have to do our derivative in terms of one variable. Remember back before Christmas we did implicit differentiation and we had problems with x's and y's. What we're going to be doing with these, since it's over time, we'll do all the derivatives with respect to time. So that means if you have a t, its derivative is just like normal. But any other variable, like if I have an x, it will get a dx dt with it. If I have a y, it will get dy dt. If I have a z, it will get dz dt. So everything else we're doing its derivative with respect to time. So kind of our strategies. A lot of these problems are going to be geometry related, so something that we might be able to draw a picture and help. So if you can, draw that picture. Record the values of the variables and the rates of change. This is probably the most important thing you can do. That's step 2, writing out what we have. Using the art diagram to find some kind of equation. You know, if I'm talking about a right triangle, what equation might pop into your mind?
A squared plus b squared equals c squared.
Yes. If I'm talking about area of a circle, what equation am I looking at?
That's pi r squared.
Pi r squared. If I'm talking about the volume of a sphere, we might use that formula. So we will have to find some kind of formula that would work in our scenario. We'll take our derivative with respect to t, and then we substitute in our values. Very important, don't substitute until after the derivative. If you substitute beforehand, what's the derivative of a constant? 0. So everything's going to go away if you plug it in too soon. So we can't plug in our values until after we do the derivative for anything that is changing. All right, so let's try an example. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So let's do a couple things here. First, do you know, well, let's look at these numbers. Your units are going to tell you a lot. When I'm looking at the units, anything that has a per second or per minute or per hour, that's a rate. So it has to be a derivative. Okay, so all the derivatives will always have per some unit of time. So this represents a derivative. Cubic centimeters is what? When do you get cubics?
Triangle.
Triangle, or if we're being more specific or more general, volume. So this is talking about how the volume changes. So I'm going to call that dV dt. It's increasing, so it's a positive 100. All right. What else do we have? My question is, how fast is the radius increasing? So I'm not asking what the radius is, I'm asking how the radius is changing. So if I'm talking about a rate of change, that's a derivative. So I am asking you to find dr dt. How is the radius changing? That's my question mark. Then I gave you the diameter. What's diameter helping me find?
Radius.
Radius. If the diameter is 50, what's my radius? 25. Is everybody okay so far? So you're welcome to draw yourself a picture if it helps here. We are looking for volume of a sphere. So this is not a formula that I would require you to have memorized, although it's going to come up a time or two, so you might know it before too long. So volume of a sphere is 4/3 pi r cubed. All right. Can I plug in my 25 right now? No, because is the radius always 25? No, because I'm pumping air into my balloon, so it's getting bigger and bigger and bigger. Now, if it was something that didn't change, if it was a true constant, like I have a soup can, does the radius of a soup can change as I'm pouring soup into it? No, so that would be a true constant, then you could plug it in. But at any value that's changing, we cannot plug in yet. So what we're going to do is find our derivative, but everything is with respect to time. So the derivative of v will become dv dt equals the 4/3 pi, that's just a coefficient. R is my variable, so the 3 comes down. 3 times 4/3 pi just gives me a 4 pi. R to the second, and anytime you do the derivative of any variable except time, we have to put the dr dt with it. That's from the implicit differentiation that we did before Christmas. Is this okay with everyone? Now we can plug in our stuff. So dv dt is 100 equals 4 pi, radius is 25 squared, and I do not know dr dt. I think I did put blank slides next to these if you need a little extra space. Okay, so 25 squared is 625 times 4 is 2,500 pi dr dt. Dr dt turns out to be 1/25 pi. I am going to ask you to put units, but your derivative is really going to help you with that. R is the radius. What was the unit on my radius? Centimeters. Per dt, time was in seconds. So my radius is increasing 1/25 pi centimeters per second.
Is this like your homework?
Mm-hmm.
Oh, I can.
Oh, this is all? Great.
It is.
Some of this economics, biology, chemistry, physics crap.
I thought that was a fun way to start back.
Yeah, so fun.
Guys, just don't. What's your definition of fun? I mean, giving you all the opportunity
Reading
to
a
teach
book.
math.
Yeah. Watching a
Oh, I do like reading a book, but Belle won't bring me a good book.
Playing with
It's
dogs.
in my locker.
What book?
I was a silent patient.
Uh-huh.
I read it in a day, I think.
Okay, I want to read it.
Oh, you've read some weird
I'm
books. You
hearing,
can't.
I'm hearing
I have,
mixed.
like 10 Years of Flesh.
I'm hearing.
Some of the stuff
is
you've
that
shown
one
me.
good?
Yeah.
I hear mixed things about both of them.
They're both good.
Some of the ones you've shown me that you've read in just graphic art. Like, some of the stuff I read is weird. Yours is weird.
Essentially.
Like
Like-
what? Very.
Okay,
To you.
suppose that x of t and y of t are the x and y coordinates at time t of a point moving around a circle. So we have this point that's just rotating around the circle. Okay, this is the x and y give you where you are at any given point in time. If I asked you to find this derivative with respect to t, so I'm not asking you to plug in any numbers yet, I just want to know, what would this derivative be with respect to t? So 2x, or x squared, would become 2x dx dt, because I'm doing it with respect to t. Derivative of y squared,
2y dy dt.
derivative of 25.
0.
So now, using this equation, look at your next slide. Suppose x is 3, y is 4, dx dt is 12. Find dy dt. So you guys do that.
You just multiply that by 6.
Oh, that's it.
It's not 6.
Oh man.
It was a 6.
I did it wrong.
What's wrong?
I accidentally flipped dy dt.
When you copied it over to
Yeah.
the slide. Well, good news is you know what you're doing. Just a minor error.
Oh, cool, that's right.
All right.
Why?
Can we try
Where is it?
something that requires more thought?
Probably. But just give me 1
I don't
second.
know, I kind of like my brain being turned off and just doing little baby magic.
Okay.
Why are you taking apart Ben's pen? Why though? Well, I'm surprised I don't see you with one of those Stanley Cups.
I'm not that basic.
Are you?
Actually, I wanted one better than that. Cabot didn't give me
Not
that.
that
I thought.
No, my mom. No, I'm kidding. I asked him for it on Christmas Eve.
Every year it's a new cup. What's the obsession with water cups?
No, I just want it because it's as big as my hydro flask, but it fits in my cup holder. But they're like $60. I'm not paying $60 for a cup.
That's
If you're gonna
silly.
use it on the daily, you might as well. It's better than $60 on something you'll blow and never use again.
Like
I
a
think
video
I
game.
paid $8
Hey,
for this
hey.
stuff. I like it.
Those games you'll play for hours.
All right, let's look at this.
Yeah,
Get
not even.
I spend $60, I get 60 hours out.
I paid Jeff.
A rocket that is launched vertically is tracked by a radar station located on the ground 3 miles from the launch site. What is the vertical speed of the rocket at the instant that its distance from the radar station is 5 miles, and this distance is increasing at the rate of
Am I a
5,000
rocket
miles per
scientist?
hour?
Is that a triangle?
It just
Okay.
keeps going on.
It just keeps going. So this is why drawing a picture and labeling things is really, really important. So let's go back. A rocket that is launched vertically. So our rocket is going up. Now we're going to assume it keeps going, right? So this is a variable. It's going to change given a point in time. Okay, here's my launch site. Here's where we launched it from. There's our launch site. This is my rocket up here.
I drew my rocket down. Okay, I'll just.
Okay, and then we have a radar station located on the ground 3 miles from the launch site. Okay, so here's my radar station. Is this a variable or is this a constant?
Constant.
Constant. So I'm going to go ahead and label that with a 3. It's always 3, that's how far apart they are. Neither one of them is moving, so that doesn't need a variable. Alright, so we have a triangle here. Now, my vertical, this is changing as the rocket moves, so I'm going to call that x. Is the distance from the radar station to the rocket changing?
Yes.
Yes, so that's going to be my y. Doesn't matter what you call those variables, because I didn't tell you in the problem, but that's also why your picture is important, so I can look at it and know what your variables are.
On your rocket.
So pretty. Overachiever right there.
Meow.
Okay. What is the vertical speed of the rocket? So which variable gives me the vertical height of my rocket?
X.
So the speed would be,
Derivative of X.
so dx
dt.
dt. That's what I am trying to find. At the instance that its distance from the radar station is 5. So what's 5 here?
X. Y.
The distance from the radar station. So that's y. So at this particular point in time, y is 5. Again, is y always 5?
No.
No, just at this time. And this distance is increasing at a rate of 5,000 miles per hour.
Oh, I know that one.
So what variable is that?
dy dt.
Mm-hmm.
Too good. I will take this test tomorrow.
Okay. So here's what I've got. Now, what kind of equation might I think about here?
Probably a squared plus b squared
Equals c squared.
So x squared plus 3 squared equals y squared. Or you can go ahead and say 3 squared is 9. Okay, so let's do the derivative of this. What is it? Mm-hmm.
2x
Plus 0. Oh,
What?
dy dt.
So far, so good? Now, I'm looking for dx dt, so I really need values to plug in for everything else. I don't know my x, I wasn't given that. I know my y is 5, and dy dt is 5,000. But am I going to be able to figure out dx dt if I still have an x here?
No.
Hey, how can I find x?
Plug y into x squared plus 3 squared plus y squared.
Yes.
So good.
We have this equation with our sides. But we know at the particular instant that I need my x, my y was 5. So at this instant in time, when my x, or when my y is 5, my x has to be 4. So I wasn't told the x, but I had all the tools I need to find it. $6,250.
Miles per hour.
Yes, x was in miles. My time is in hours.
I'm so good at this.
Isn't this fun? I love these problems.
I'm ready to take the test tomorrow.
No, you're not. I'm not.
Say that, please.
No, it's just funny because I said that to Miss Fuller this morning, and she goes, I wouldn't. Like, I was feeling so confident. She goes, I wouldn't.
Not
I
really.
was like, okay.
She will look at your work. You're wrong in every way. Again.
Miss Fuller loves me.
Does she?
Yeah, she do.
All right, one last problem for today.
I'm
She has like a
definitely-
hate journal of that.
definitely her
You'll
favorite.
feel well.
She,
All right, let's try this one. This will be be our last
Do
one
not
for
make
today.
that your favorite.
Why don't you guys take a second and see how far you can get? See if you can draw a picture, label variables, and then we'll check it before you actually work everything out. So, did you all draw a triangle?
Yeah.
Okay. The ladder, which side is the ladder?
Hypotenuse.
Okay.
That is the terminology.
Is it changing or is it constant?
Constant.
So, I can go ahead and label this as 10. It doesn't need a variable because it's not changing. Alright, so these other sides, what's happening is this ladder is sliding. It's going to come down and away. Okay, so these are changing. So they need variable names. I'll call them X and Y.
Yes, they're the same.
So the bottom is sliding away from the wall at a rate of 1 foot per second. Anytime if I look at those units, feet per second, that's a rate. So this is a derivative. It's a derivative of what? dy dt. Okay, what am I looking for? When the bottom of the ladder is 6 feet from the wall, what's that represent? Mm-hmm. Can we go ahead and find x even though it wasn't given? Yeah, so at that particular instant, x squared plus 6 squared equals 10 squared. So at that particular, what did I do?
Yeah, that is not the right answer.
No, I was jumping ahead. I looked at it and knew it was going to be a 6, 8, 10 triangle, and then
6, 8, 10. Okay.
so x is 8. Sorry, sometimes I get ahead of myself.
6,
So-
8, 10. So we call it that.
My equation: x squared plus y squared equals 10 squared, or 100. What's the derivative of this?
2x dx dt plus 2y dy dt equals 0.
Okay. And we plug in.
How did I mix that up as 128?
What?
I thought that when I wrote my parentheses, when I read it, I thought it said 228, not, or 128, not
Instead
2.
of 2 times.
I don't know. I don't know.
What would our units be?
Feet per second.
Why is it negative?
Come down.
Because it's coming down. Yeah. All right. Is this okay? Off to a decent start?
Yeah.
So you are ready for your
Test.
test
Homework.
tomorrow.
Yep.
Or you can do the day 1 homework.
Homework.